Hello everyone, this is Dr. Young, and we are going to try to wrap our minds around the acidity of the alpha hydrogens, or in other words, the hydrogens that are on those alpha carbons. Because it turns out that it's really, really important and that we can take advantage of that acidity to do a lot of different transformations at the alpha carbon of a carbonyl. So let's take a look and see what we're talking about here. So the alpha position, let's just remind ourselves about the alpha position. We've talked about this before, but again, it's a really important part of a molecule when you have these carbonyl compounds. Remember that the alpha, beta, gamma, delta, that system, it just refers to how many carbons away are you from a certain functional group. So like in my first one, I have a ketone. So I want to know how many carbons away are we from that, right? So that's where my carbonyl is. That's the ketone. So 1 away would be alpha. 2 away would be beta. 3 away would be gamma. And then I can go out to the right-hand side, right? Because that's still 1 away. That's also an alpha. This is also a beta, but I don't have a gamma going off to the right-hand side. And so I can talk about these alpha positions. I can talk about the alpha carbon or the alpha hydrogen, right? So like this right here, right, that's an alpha carbon. And on it, it looks like I have 2 alpha hydrogens, right? I'll have one hydrogen here, one here. So I have 2 alpha hydrogen atoms. I could look over on the right-hand side and say the same exact thing, right? That's the alpha carbon. And that is, then this alpha carbon has 2 alpha hydrogens. Now for this video, right, I'm really interested in the acidity of the alpha hydrogens. So I'm just going to start talking about things in terms of alpha hydrogens. So if I look at this molecule on the right-hand side, the cyclopentanone, same deal, right? It looks like I have an alpha hydrogen here, and sure enough, I do have 2 alpha hydrogens on this one, right? There's an alpha hydrogen, here's one, here's one. So altogether, I have 4 alpha hydrogens coming off of this molecule, right? These are all alpha hydrogens. Now, if I look over at my aldehyde, if I go to the next one, I've got my aldehyde group right here. Let me see if I can get this for you right. So here's my aldehyde, the carbonyl in my aldehyde. And I have, if I go to the left-hand side, I have an alpha hydrogen, or alpha carbon, beta carbon, gamma carbon. But you'll notice that if I go to the right, I do not have an alpha carbon, and therefore no alpha hydrogens on the right-hand side. I know there's an H in the alpha spot, or like the 1 away from spot, but there's no carbon coming off of it, right? The idea is that the alpha hydrogens come off of the alpha carbons, right? The carbon right here needs to be having hydrogens on it. There's no carbon there, so there's no alpha hydrogens. So right here, right, this is not, let me write here, this is not an alpha hydrogen. That's not an alpha hydrogen, and right here, we do have 2 alpha hydrogens. And then if I look at the last molecule right here, right, again, I've got my carbonyl, I've got an alpha spot right here, an alpha spot right here, but in this case, there aren't any hydrogens coming off of that carbon at all, right? So this molecule has, this molecule has no alpha hydrogens whatsoever. So all of this acidity stuff that we're talking about doesn't apply to this molecule. Even though it has alpha carbons, it has no alpha hydrogens. Right? So I just want to point that out. So what's so special about the alpha position, right? So again, if I take a look at these molecules, here's my alpha, here's my beta, alpha, beta, alpha, alpha, beta, beta. And let's say, for example, we're talking about the acidity of one of these beta hydrogens, right? So I'll just take one of these 3, right? There's 3 here. Let's just talk about one of those coming off. If that acts as an acid, I'm going to have, right, 2 hydrogens on here still, and then a negative charge and an H+. That's what the reaction would look like, right? If we're talking about it acting as an acid, where the H+ comes off. And that would be in the beta spot, right? So this is beta. And let's compare that to if I removed an alpha hydrogen instead. So let's just pick this one on the right-hand side. So let's look at one of these alpha hydrogens. I'll say we'll take one of those off. Still have an H. And now I have a lone pair there and a negative charge, and again, plus the H plus. And so now we're talking about the alpha hydrogens. Now, if I look up here, right, if I ask myself, well, how stable does this sucker look, right? Here I have a negative carbon, which we should remember, right, from back in like chapter 3 for our book, but long, long time ago, right? So this is a negative carbon, which is bad, right? It's not very electronegative. It's not very electronegative, so it's not very, very, very stable, right? And I'll put sort of in parentheses here, right? We would say that this thing probably has a pKa greater than 50. Like it's really, really high. Very, very, very high. It's just a negative carbon. Terrible. If I take a look at this one down here, it's the same story. I have a negative carbon, which again is bad. It's not stable. It's really high in energy because carbon's not very electronegative. It doesn't want to be negative. But the big difference here is that this is right next to that carbonyl, right? It's in the beta, or it's in the alpha spot. So this lone pair can actually drop down and go up into the carbonyl, and we'll see that it's actually delocalized, right? It's not a negative carbon just stuck on one place. It can actually be delocalized to make this, right? So I'm able to delocalize that negative charge and spread it out over more atoms. And in fact, if you take a look at this, right, the original thing I drew is actually the minor contributor, the minor resonance contributor, and the bottom one is the major resonance contributor, right? Because I'd rather have a negative on the O than the C. So if I take a hydrogen off of the alpha carbon, right, if I take off one of those alpha hydrogens, it's not just that I have a negative carbon, which is terrible, it's that I actually mostly have a negative oxygen, right? So if I look at this molecule, it's mostly a negative oxygen and partially a negative carbon. Right, which is going to be much, much more stable, much, much more stable because you have the negative on an oxygen, right? So that's going to make this more stable than that beta hydrogen being removed. Much, much more stable. If I drew the real molecule, let me express this a different way. If I drew the real molecule, this thing would look like, all right, oxygen, there's some double bond. The double bond's mostly here, a little bit. Or sorry, actually, other way around. The double bond, right, it's mostly an alkene here. So it's mostly an alkene here, a little bit of carbonyl there. And then the negative charge is on the carbon a little bit, but mostly on the oxygen, right? It's much larger on the oxygen. So I try to draw just a bigger delta there. So it's mostly a negative O, but just a little bit of a negative C. And just by having a carbonyl next to that carbanion so that it can delocalize, right, so it can be resonance stabilized, now the pKa goes from 50 to about 20. So it drops like crazy. It's way, way, way more stable of an anion than the one before. We're talking 30 pKa units, right? Remember, this is a log scale, so this is 10 to the 30th difference in acidities and their equilibrium constants. So that's a huge difference. So they're relatively acidic. They're not too hard to remove, actually. So let's kind of compare that to some other things. Now again, right, we're talking about this hydrogen here. They're talking about the alpha spot. So here's an alpha carbon. So we're talking about these hydrogens here, right? The two here and the two here. This is a table I just got from University of Calgary. You can check out that link there if you want. But here are here's the alpha carbons that we're looking at. So these suckers, right? All of those are alphas, right? Here's the alpha carbon next to a carbonyl, next to an aldehyde, next to a ketone, next to an ester, next to a nitrile. We'll talk more about nitriles later, and next to amides. But you can imagine nitriles will do the same thing. They can also delocalize, using resonance structures. They can delocalize into the C triple bond N. But you'll notice that, like I said before, that the ketone was about 20. The aldehyde was a little bit lower. It's more acidic because it's a more electron poor carbonyl, so it can take more of those electrons, it can accept more electrons. Things like amides are more electron-rich carbonyls, so they're not as able to pick up to accept electrons more. They're more electron-rich already, so they don't stabilize the anion as much, so their pKa's are higher. So let me maybe we'll just write that off to the side here. That's right, more acidic. And that's because aldehydes are less electron-rich. I'm going to do it in a different color. Right? Since they're less electron-rich, they're more able to pull electrons in and do that delocalization we were just talking about. Less electron-rich, right? So the less electron-rich a carbonyl is, the better able it is to delocalize those electrons, that negative charge, into the carbonyl or the pi system that we're talking about here. And now that's not, and I'm glad that this is up here. So it doesn't make you as acidic as something as like a carboxylic acid, which is all the way down at 5. But it's not as bad as if you have an alkane, which is all the way up in the 50s, right? So like I was saying before, that beta over there on the previous slide, that was up in the 50s probably. But it's not as good as having a negative on 2 O's like a carboxylic acid. So here's kind of where they fit in. I think that what you should think when you see an alpha hydrogen, I think you should think of these pKa's, if you're remembering them, as being about 25-ish. And if you think about any of the carbonyls as being about 25-ish, that's going to give you a good sense of about where these alpha hydrogens are going to show up, right? Some are a little more acidic, some are a little less acidic, but 25 is a good rule of thumb number for your alpha hydrogens. So let's take a look at, kind of a ranking thing. How do these rank compared to some other things? And maybe some reagents that we could use to totally deprotonate these alpha positions. Now, rank the following from least to most acidic, right? We can go with pKa's. If you've memorized pKa's, you can just go lay these out there and go 1, 2, 3, 4. But I just want to go again, kind of review for you how we can look at these without knowing pKa's, just based on how stable is their conjugate, right? Because if I look at these molecules, I'm not 100% sure what these would look like or how they would rank in terms of acidity. But if I turn them into their conjugates, I can definitely think about how stable one thing is versus another, right? So if I look at the conjugate of each one of these acids, so here's the conjugate base of this acetic acid, right? So we're saying if it loses an H+. Same thing for this one, if we lose an H+, so I have, here's my alpha one actually. For this one, I'm going to lose the H in the middle, and we'll see why in a second. And this last one, it doesn't matter which H I lose. Let's just say I lost an H out here. For that, what is that? 1, 2, 3, 4, 5, 6, 5 pentane thing. For any of these, and the H here. So if you're looking at any of these, you'd first notice, right, that, well, oxygen is very different than a negative carbon, right? The 3 on the right are all negative carbons. First one's a negative oxygen, so that kind of automatically just wins, right? We have a negative O. And more specifically, if I look at this, it has electron delocalization, so I can say that I also need to think about the molecule looking like this. Same thing here. If I have this drop down and that kick up, that has electron delocalization. And what's nice about this one, the reason I took off the middle one, is because I can draw actually 2 more resonance structures, right? Because I can have one where the electrons drop off to the left, which will give me this enolate. All right, O minus, double alkene there, double bond there. And I can have it go into the other carbonyl, right? So I can have these drop down, the alkene move over and kick up to give me the other carbonyl as turning into the enolate. All right, so I actually have more electron delocalization here. And then if I look at the last one, there's no delocalization whatsoever, right? It's not alpha to any carbonyls. There's nowhere for that to go. So right off the bat, hopefully you're looking at that and being like, well, that's terrible, right? This is the least stable. This is the least stable, and therefore that's the worst acid, right? Because it's hardest to make that lose a hydrogen. So that's the worst acid right off the bat. So I'm just going to call that my 4. This is my number 4. Not great. Now for the rest of these, again, so for the first one, I have a negative on an O and a negative on an O. That's pretty good, right? This is like a negative charge on 2 oxygens. That's looking real good to me. The second one is a negative charge on an oxygen and a carbon, which is not terrible. I'd rather not have a negative on a carbon. I'd rather it only be on oxygen. And then for this third one, I have a negative on a carbon and 2 oxygens. So that should be the most stable, right? Because I have the negative charge on 2 oxygens instead of just on 1 oxygen and a carbon. So I probably have the contributor with the negative on the carbon is probably the least. It's the most minor contributor, and so it has a less influence on the actual stability and the actual structure of the real molecule. So just looking at that, then I should be able to say that, okay, the carboxylic acid one's going to be my number 1. This one should be number 2, and this one should be number 3, right? So the alpha hydrogen was better than not being a hydrogen. This one, and I'll refer to these again later, but I think of that as kind of being doubly alpha, right? Because it's like alpha to the left carbonyl and it's alpha to the right carbonyl. We'll talk about how these are beta dicarbonyl systems in future videos, but being doubly alpha gives you more resonance structure, so you just become more stable. It's just even easier to remove you. And so my ranking would be 1, then 3, then 2, then 4, right? My most acidic is where I only have negative oxygens. My second most acidic is where I have 2 negative oxygens and 1 negative carbon. Third most acidic is where I have a negative carbon mostly, but a little negative carbon. And then the number 4 is only negative carbon, so that'd be the worst. Now, what's going to start becoming important to us in the next videos, right, in the next lectures here is once we make this carb anion, this enolate ion, when we remove the alpha hydrogen, then we can start adding stuff to the molecule. Because right now, once it becomes negative, then it becomes a nucleophile. And once it becomes a nucleophile, we can start adding things onto it. We can start having things attached there, which is going to be important. So in this second question, I'm asking which base or bases will completely deprotonate this ketone. And when I say completely deprotonate, what I mean is that the base it's a very strong base. So a very strong base. So if I look at the first one, this is butyl lithium, right? This is basically like having a negative carbon and a positive lithium. So it is a very strong base. That would absolutely work to deprotonate a hydrogen in an alpha spot here, right? Alpha hydrogen, alpha hydrogen. It would be a very, very strong base. It would absolutely deprotonate that. Its pKa is really high. Oh, speaking of pKa's, just for those of you who are remembering pKa's, carboxylic acids have pKa's of around 5. Let me write that up here. So pKa of around 5-ish or so, depending on what's on them. Again, we just said that we're going to call our alpha hydrogens about 25. The dicarbonyls, right, so pK of these drop down to like 10 to 12, so they get quite acidic. And then lastly, again, alkanes are above 50, 55, something like that. They get real, real high. So our ranking should have gone in order of the pKa's, and sure enough, it does. Butyl lithium, right, like we said, had a pKa of around 55-ish or so. So that means it's a much stronger base. It's definitely able to take off hydrogens of something that has a pKa of around 25. So absolutely that would remove that hydrogen. LDA, right, you might remember LDA is lithium diisopropylamide. So lithium diisopropylamide. So you've got a negative lithium and a positive lithium and a negative diisopropylamide. Negative N, those things have pKa's of around 35-ish, right? The amines are like 35. That's also above 25, so that would work also. that would completely deprotonate that ketone. There wouldn't be any parent ketone left. It would all be enolate. It would all be removed. If I look at T-butanol, right, T-butoxide, not T-butanol, T-butoxide, alcohols, if you remember, have pKa's more like 15 or 16. And so this would not, right? That pKa is lower than 25. So this would not completely dissociate it. It would only take off like a small percentage of the alpha hydrogens, which is enough for us to get things to happen. But we'll talk more about the reactions that involve the strong bases as opposed to the really, really strong bases. But it would take off a little bit, but not all of it. It would mostly still be ketone, right? It'd still mostly be ketone. This pKa is too far off. And then it's the same story for hydroxide, right? Hydroxide's same thing, 14, 15, somewhere in there. And it's just an O minus. So if we were going to look at this then, right, hydroxide, like we were saying, is just another O minus. So it also would not fully deprotonate this molecule. So remember, the big takeaways here are just that you want to keep in mind that those alpha hydrogens are relatively acidic for CH bonds. You can use these really strong bases to deprotonate them, and what we're going to do is we're going to see that we can now take those enolates that we just formed and then add things to them like alkyl groups or halogens or acyl groups or something like that. So that's what we're going to see in our next videos. So make sure you got good notes for this. Let me know if you have any questions. Happy studying and good luck.